Hello there, and welcome to Cosmic Slumber. Tonight we are drifting toward one of the strangest, quietest places in the entire universe, a black hole. Space itself carries no sound, not in the way we experience it here on Earth, and yet astronomers have found ways to listen anyway, translating ripples in gas, light, and the fabric of space itself into tones a human ear can actually hear. Some of those tones are so deep they sit far below anything a human voice could ever produce. Some are quick, rising chirps lasting only a fraction of a second. The sound of two black holes finally colliding after spiraling toward each other for millions of years. This video has no adverts and no interruptions, just a slow, steady drift into the sound of some of the darkest, most silent objects known to exist. If you enjoy these gentle journeys, I invite you to like, subscribe, or leave a thought below. It helps other sleepy minds find their way here, too, one quiet echo at a time. But for now, all you need to do is relax. Let your shoulders soften. Let your eyes grow heavy. Let your thoughts sink slowly downward, past starlight, past silence, into the deep, low hum where a black hole is quietly, patiently turning in the dark. Let's begin. Space itself is almost entirely silent, because sound needs a medium like air or gas to travel through. Unlike light, which can travel through the emptiness of a vacuum, sound waves need particles to bump into one another in order to move from one place to another. Because most of space is such an extreme vacuum, ordinary sound as we experience it on Earth simply cannot travel across the vast, empty stretches between stars and galaxies. Despite that near-total silence, astronomers have detected genuine sound waves near a distant black hole, moving through hot gas surrounding it. In a galaxy cluster called Perseus, roughly 250 million light-years away, scientists identified real pressure waves rippling outward through the hot gas surrounding a supermassive black hole at the cluster's center, sound waves in the truest physical sense, simply traveling through gas rather than through air. The sound waves detected near the Perseus black hole are almost unimaginably deep, far too low for any human ear to hear directly. Researchers calculated the pitch of these waves to be roughly 57 octaves below middle C, a note so profoundly low that it falls more than 1,000,000 billion times beneath the lowest sound the human ear can perceive, making it one of the deepest notes ever detected anywhere in the known universe. To make the Perseus black hole sound audible to human ears, scientists had to raise its pitch by an enormous number of octaves. Because the original sound waves were so far below human hearing range, NASA researchers scaled the pitch upward by quadrillions of times, finally producing an eerie, deep, resonant tone that human ears can actually perceive, a translation rather than a direct recording, but grounded entirely in genuine physical sound waves measured within the cluster's hot gas. The Perseus black hole sound waves have likely been rippling outward through the surrounding gas for roughly 2.5 billion years. Because the pressure waves detected by researchers appear to have originated from ancient eruptions linked to the black hole's activity, astronomers estimate this deep, resonant hum has been quietly spreading through the galaxy cluster for an almost incomprehensible span of time, far longer than complex life has even existed on Earth. The sound waves rippling through the Perseus cluster help keep the surrounding gas unusually hot, in a way that puzzled astronomers for years. Before this discovery, researchers were unsure why gas within galaxy clusters like Perseus remained so much hotter than expected. The steady outward pressure of these sound waves, driven by the central black hole's activity, appears to help continuously reheat the surrounding gas, offering a genuinely elegant explanation for a long-standing astronomical mystery. Black holes themselves do not directly produce sound in the way a musical instrument or a voice does. Rather than generating sound through vibration the way ordinary sound sources on Earth typically do, the sound waves associated with black holes usually arise from surrounding material, gas, plasma, or the immense energy released by nearby cosmic events, meaning the black hole itself remains, in the most direct sense, entirely and permanently silent. Gravitational waves, ripples in the fabric of space and time itself, are not sound waves, though scientists often convert them into audible tones for easier understanding. Gravitational waves are a genuinely different physical phenomenon from sound, involving actual distortions in spacetime predicted by Einstein's theory of general relativity, but because their frequency happens to fall within a range similar to audible sound, scientists frequently convert detected gravitational wave signals into audio as a helpful, intuitive way to represent the data. The first confirmed detection of gravitational waves came from the collision of two black holes, producing a distinctive rising tone nicknamed a chirp. When two black holes spiral together and finally merge, they release a burst of gravitational waves that rises rapidly in both frequency and intensity in the final moments before collision, producing a short, rising chirp sound once converted into audio, one of the most iconic sounds in the modern history of astrophysics. This first gravitational wave detection was made in 2015 by an instrument called LIGO, standing for the Laser Interferometer Gravitational Wave Observatory. Using incredibly sensitive laser-based instruments capable of detecting distortions in spacetime far smaller than the width of a single proton, LIGO successfully measured gravitational waves generated by two black holes merging over 1 billion light-years away, confirming a prediction Einstein had made exactly a century earlier. The black hole merger detected by LIGO in 2015 lasted only a fraction of a second once converted into audible sound. Despite representing the culmination of a slow, gradual spiral lasting many millions of years, the final, most intense moments of the two black holes actually merging together produced a signal lasting only about 0.2 of a second once translated into sound, a remarkably brief audible echo of an extraordinarily long cosmic process. The two black holes detected in that first landmark 2015 merger were each tens of times more massive than our Sun prior to their collision. The two black holes involved carried roughly 29 and 36 times the mass of the Sun respectively, merging together into a single, larger black hole while releasing an amount of energy so immense it briefly outshone, in terms of pure power output, every star in the observable universe combined. An enormous amount of energy from that black hole merger was released purely as gravitational waves, rather than as light. Because black holes do not emit light directly, virtually all the energy released during their collision took the form of gravitational waves rippling outward through spacetime itself, an entirely invisible form of energy release that light-based telescopes could never have detected on their own. Gravitational wave detectors like LIGO work by measuring incredibly tiny changes in distance between mirrors positioned kilometers apart. As a gravitational wave passes through Earth, it very slightly stretches and compresses space itself, causing a correspondingly tiny shift in the distance measured between precisely calibrated mirrors. These shifts are astonishingly small, smaller than the width of a proton, requiring extraordinarily sensitive equipment to detect it all. Since that first detection, scientists have recorded the chirp sound of many additional black hole mergers occurring throughout the universe. Following the initial breakthrough detection in 2015, gravitational wave observatories around the world have identified numerous additional black hole collisions, each producing its own distinct rising chirp once converted into sound, gradually building an entirely new way of listening to some of the most violent events in the cosmos. Different black hole mergers produce chirps with distinctly different pitches and durations, depending on the mass of the black holes involved. Generally speaking, mergers involving smaller black holes tend to produce a higher-pitched, faster chirp, while mergers involving considerably larger black holes tend to produce a lower, slower, more drawn-out tone, meaning each merger carries something like its own unique acoustic signature once translated into sound. Neutron-star collisions, closely related to black hole mergers, have also been detected through gravitational waves and converted into audible chirps. In addition to black hole mergers, gravitational wave observatories have successfully detected the collision of two neutron stars, an event that also produced a distinct rising chirp sound, alongside an accompanying burst of light that allowed astronomers to observe the very same event using traditional telescopes as well. Black holes themselves are regions where gravity has become so extreme that nothing, not even light, can escape once it crosses a boundary called the event horizon. Because light cannot escape a black hole's gravitational pull once it crosses this boundary, a black hole appears, quite literally, as an area of total darkness, a region from which absolutely no direct light, and therefore no directly observable image, can ever reach an outside observer. Despite their name, black holes are not empty holes in space, but rather regions containing an enormous concentration of mass compressed into an extremely small volume. Rather than representing literal emptiness, a black hole packs a substantial amount of mass into an incredibly compact space, creating gravity so intense that the surrounding spacetime itself becomes dramatically warped and distorted around it. The boundary of a black hole, called the event horizon, is not a physical surface in any conventional sense. Rather than representing a solid boundary an object could physically touch, the event horizon marks the specific distance from the black hole center beyond which the escape velocity needed to break free exceeds the speed of light itself, an invisible mathematical boundary rather than any kind of tangible physical wall. Material falling into a black hole often forms a swirling, superheated disk called an accretion disk before finally crossing the event horizon. As gas, dust, and other material spiral inward toward a black hole, friction and gravitational forces heat this material to extreme temperatures, causing it to glow brightly across various wavelengths of light, often making the area immediately surrounding a black hole considerably easier to detect than the black hole itself. The accretion disk surrounding an actively feeding black hole can be one of the brightest objects in the entire universe. Quasars, among the most luminous objects known to astronomers, are powered by supermassive black holes actively pulling in surrounding material, generating accretion disks so intensely bright they can outshine the combined light of every star within their host galaxy, visible across truly enormous cosmic distances. Some black holes launch powerful jets of material outward at speeds approaching the speed of light. Rather than everything nearby simply falling directly into a black hole, some material instead gets redirected outward along the black hole's rotational axis, forming narrow, extremely energetic jets that can extend for thousands of light years, driven by complex interactions between the black hole's spin and its surrounding magnetic field. The very first direct image of a black hole was captured in 2019, showing the glowing ring of material surrounding the black hole at the center of a distant galaxy called Messier 87. Rather than photographing the black hole itself, which remains fundamentally invisible, this landmark image, created using a global network of radio telescopes working together, captured the glowing accretion material surrounding the black hole shadow, offering humanity's first ever direct visual confirmation of what a black hole's immediate surroundings actually look like. That first black hole image required linking telescopes from locations spread across the entire planet, effectively creating a telescope roughly the size of Earth itself. Known as the Event Horizon Telescope Project, this ambitious effort combined data collected simultaneously from radio telescopes on multiple continents, synchronized with extraordinary precision, allowing astronomers to achieve a level of resolution that no single telescope alone could ever have possibly achieved. A second black hole image, released in 2022, revealed the black hole located at the very center of our own Milky Way galaxy, known as Sagittarius A star. Considerably closer to Earth than the black hole in Messier 87, though still located roughly 26,000 light-years away, this second landmark image confirmed the presence of a supermassive black hole anchoring the gravitational center of our own home galaxy. The supermassive black hole at the center of our galaxy is estimated to contain roughly 4 million times the mass of our Sun. Despite this staggering mass, Sagittarius A star remains relatively quiet and inactive compared to many other known supermassive black holes, consuming surrounding material at a comparatively slow, modest rate, rather than blazing brightly as an actively feeding quasar might. Stars orbiting near the center of our galaxy move at extraordinary speeds, offering strong indirect evidence of Sagittarius A star's presence long before it was ever directly imaged. By carefully tracking the rapid, tightly curved orbits of stars swinging closely around the galactic center over multiple decades, astronomers were able to calculate the presence and mass of an invisible, extremely compact, extremely massive object well before any direct image confirmed exactly what that object actually was. Falling into a black hole would theoretically stretch an object extremely thin, a dramatic and mercifully hypothetical process nicknamed spaghettification. Because gravity near a black hole becomes so much stronger at closer distances, an object falling in feet first would experience considerably stronger gravitational pull on its feet compared to its head, theoretically stretching the object into an increasingly long, thin shape as it approaches the black hole center. Time itself would appear to slow down dramatically for an object approaching a black hole's event horizon, according to Einstein's theory of general relativity. From the perspective of a distant outside observer, an object falling toward a black hole would appear to move increasingly slowly as it neared the event horizon, seeming to freeze in place indefinitely at the boundary, rather than ever appearing to actually cross it, a genuinely strange consequence of how gravity bends time itself. From the perspective of the object actually falling into the black hole, however, that same crossing would likely happen relatively quickly and without any dramatic, noticeable pause at all. While a distant observer would perceive time appearing to freeze at the event horizon, the object doing the actual falling would, according to theoretical predictions, cross that same boundary in relatively ordinary, unremarkable fashion from its own particular point of view, one of general relativity's more genuinely mind-bending implications. Black holes are believed to eventually, extremely slowly, lose mass and energy through a theoretical process known as Hawking radiation. Proposed by physicist Stephen Hawking, this process suggests black holes are not perfectly eternal, but instead emit a faint stream of particles over extraordinarily long timescales, gradually losing mass in a process so slow that no black hole currently in existence has had anywhere near enough time to noticeably shrink because of it. The smaller a black hole is, the faster it is theoretically predicted to lose mass through Hawking radiation. According to current theoretical models, smaller, less massive black holes would evaporate considerably faster than larger, more massive ones, meaning an extremely small, hypothetical black hole could theoretically evaporate relatively quickly, while a supermassive black hole would require a timescale vastly longer than the current age of the universe itself. Black holes come in a wide range of sizes, generally categorized into several broad groups based on their overall mass. Astronomers generally classify black holes into categories including stellar mass black holes, formed from the collapse of massive dying stars, and supermassive black holes, found at the centers of galaxies, with mass ranging anywhere from a few times that of our Sun up to billions of times greater. A category of black holes known as intermediate mass black holes has proven considerably more difficult for astronomers to directly detect and confirm compared to smaller stellar mass and larger supermassive black holes. Sitting somewhere between stellar mass and supermassive black holes in terms of overall size, these intermediate objects have remained comparatively elusive, with only a relatively small number of strong candidate detections confirmed by astronomers so far. Nearly every large galaxy studied so far, including our own Milky Way, appears to contain a supermassive black hole at its very center. Based on extensive observational evidence gathered across a wide range of galaxies, astronomers now generally believe that most, if not effectively all, large galaxies host a supermassive black hole anchoring their gravitational center, suggesting a close, fundamental relationship between galaxies and the black holes residing within them. The relationship between a galaxy and its central supermassive black hole appears closely intertwined, with each seemingly influencing the other's growth and development over cosmic time. Observational evidence suggests a galaxy's overall size and the mass of its central supermassive black hole tend to correlate fairly closely, leading many astronomers to believe galaxies and their central black holes likely grow and evolve together across billions of years, rather than developing entirely independently of one another. Black holes cannot be seen directly, but their presence can often be confirmed through their gravitational effect on nearby visible matter. Because a black hole itself emits no light, astronomers typically detect its presence indirectly, observing the motion of nearby stars, gas, or other visible material being gravitationally influenced by an otherwise completely invisible, compact object hidden at the center of that observed motion. Some black holes are detected through the powerful X-rays emitted by superheated material swirling within their surrounding accretion disk. As material spirals inward toward a black hole, friction and gravitational compression heat it to temperatures extreme enough to emit X-ray radiation, providing astronomers using specialized X-ray telescopes with another valuable, indirect method for detecting and studying black holes scattered throughout the universe. Black holes were first seriously theorized well over a century ago, based on the mathematics of Einstein's theory of general relativity, though considerable skepticism about their actual existence persisted for many decades. Although the underlying mathematics permitting black holes emerged shortly after Einstein published his theory of general relativity, many scientists, including Einstein himself at various points, remained skeptical for years that such extreme objects could genuinely exist within the real, physical universe. The term black hole itself was popularized relatively recently in the broader history of the underlying science, gaining widespread use largely during the 1960s. Although the underlying theoretical concept dates back considerably further, the specific term black hole only became widely popularized starting in the 1960s, helping introduce this genuinely strange astrophysical concept to a much broader general public audience for the very first time. Stellar mass black holes form when an extremely massive star exhausts its fuel and its core collapses under the force of its own gravity. When a star many times more massive than our Sun reaches the end of its life, its core can collapse so completely and so rapidly that not even the extreme pressure supporting a neutron star can halt the process, resulting instead in the formation of a genuine black hole from the star's own collapsing remains. Not every massive star's death results in a black hole, since the exact outcome depends heavily on the star's original mass and how the surrounding supernova explosion unfolds. Depending on precisely how massive the original star was, and exactly how the resulting supernova explosion plays out, a collapsing stellar core may instead form a neutron star rather than a black hole, meaning the boundary between these two very different possible outcomes remains an active area of ongoing astrophysical research. Some of the earliest black holes may have formed directly from the collapse of gas within the very early universe, rather than from the death of a star at all. Certain theoretical models propose that some black holes, sometimes called primordial black holes, may have formed directly from unusually dense regions of gas collapsing shortly after the Big Bang itself, entirely independent of the stellar life cycle responsible for forming the vast majority of black holes known today. Gravitational wave detectors have occasionally recorded black hole mergers involving black holes considerably more massive than astronomers initially expected based on prior stellar evolution models. Some detected mergers have involved black holes whose individual masses sit within a range that standard stellar evolution theory suggests should be surprisingly difficult to produce through the typical collapse of a single massive star, prompting astronomers to explore alternative formation pathways, including the possibility of earlier black hole mergers combining to reach such unusually large individual masses. Black holes can, in certain circumstances, merge with other black holes multiple times across cosmic history, gradually building up considerably larger black holes over many successive collisions. Rather than always forming through a single, isolated stellar collapse, some larger black holes detected through gravitational waves may actually represent the product of several earlier successive mergers, gradually combining smaller black holes into progressively larger ones across an extended span of cosmic time. The sound of a black hole merger, once converted into audio, has occasionally been compared informally by scientists and journalists to a bird's chirp or a brief, rising musical note. Because the characteristic rising pitch and short duration of a converted gravitational wave signal resembles certain natural sounds familiar to human ears, the informal nickname chirp has become widely adopted throughout the broader gravitational wave research community, helping make an otherwise highly technical signal considerably more intuitive and relatable for general audiences. Multiple gravitational wave observatories now operate around the world, working together to more precisely pinpoint the location of detected black hole mergers within the sky. Beyond the original LIGO facilities in the United States, additional gravitational wave detectors, including Virgo in Italy and Kagura in Japan, now work in coordination with one another, allowing scientists to triangulate the approximate location of a detected gravitational wave source considerably more precisely than any single detector working entirely alone ever could. Future gravitational wave observatories planned for deployment in space are expected to detect an entirely new range of black hole mergers not currently observable from detectors here on Earth. A planned space-based gravitational wave observatory, involving spacecraft separated by millions of kilometers, is designed specifically to detect lower-frequency gravitational waves associated with considerably larger, slower black hole mergers, a category of cosmic collision entirely beyond the current detection range of ground-based observatories like LIGO. Black holes do not actively suck in surrounding material the way popular depictions sometimes suggest, but instead simply exert a strong gravitational pull similar in basic principle to any other massive object. If our Sun was somehow instantly replaced by a black hole of precisely equal mass, Earth's orbit would remain essentially unchanged, since a black hole's gravitational influence at a comparable distance behaves according to exactly the same basic principles as gravity produced by any other object of equal mass, without any additional mysterious sucking effect involved at all. The danger posed by a black hole is generally limited to a relatively close range, specifically near its event horizon, rather than extending dramatically further outward than the object's mass alone would predict. Because a black hole's gravitational pull follows the very same fundamental rules governing gravity everywhere else in the universe, meaningful danger only becomes significant at a genuinely close distance, near the black hole's event horizon itself, rather than posing any unusual additional threat from a considerably safer distance further away. Black holes emit no light of their own, meaning their presence can only ever be confirmed through indirect observational evidence of one kind or another. Because a black hole itself produces absolutely no direct light, astronomers must always rely on some form of indirect evidence, whether gravitational influence on nearby objects, emitted X-rays from surrounding material, or gravitational waves detected from a merger event, in order to confirm and study black holes scattered throughout the observable universe. The idea of listening to the universe, rather than only looking at it, has opened an entirely new scientific field known as gravitational wave astronomy. Prior to the first confirmed detection in 2015, astronomers relied almost exclusively on various forms of light to study the universe. Gravitational wave astronomy introduced an entirely new, fundamentally different way of gathering cosmic information, allowing scientists to, in a very real sense, begin listening to previously invisible cosmic events for the first time in the history of the field. Some astronomers describe the emerging field of gravitational wave astronomy as adding a genuinely new sense to how humanity studies the universe. Much like adding hearing alongside sight dramatically expands a person's overall awareness of their immediate surroundings, gravitational wave astronomy is often described by researchers as adding an entirely new, complementary sense to the broader practice of astronomy, allowing scientists to detect certain cosmic events that would otherwise remain completely invisible using light-based telescopes alone. Black hole mergers detected through gravitational waves can sometimes be confirmed and further studied using traditional light-based telescopes as well, when the surrounding conditions happen to allow it. While black hole mergers themselves typically produce no directly observable light, certain related events, such as neutron star collisions, can produce both gravitational waves and a corresponding burst of light, allowing astronomers to study the very same cosmic event using multiple entirely different, complementary observational methods simultaneously. This combined approach, using both gravitational waves and traditional light-based observation together, is sometimes referred to by astronomers as multi-messenger astronomy. By combining data gathered through gravitational waves with data gathered through traditional telescopes observing light across various wavelengths, astronomers can build a considerably more complete, detailed picture of major cosmic events, drawing on multiple independent, complementary messengers of cosmic information simultaneously. The sound of gravitational waves detected from black hole mergers has been used in various public outreach and educational efforts to help make an otherwise highly technical scientific discovery more broadly accessible and relatable. Because an audible chirp is often easier for a general audience to intuitively grasp compared to a purely visual graph or complex mathematical description, gravitational wave researchers frequently use these converted audio clips specifically within educational and public outreach materials, helping communicate the excitement and significance of this discovery to a considerably broader general audience. Black holes can theoretically rotate, spinning rapidly around their own axis in a manner that meaningfully influences the surrounding spacetime itself. A rotating black hole, sometimes described using a specific theoretical solution known as the Kerr metric, drags the surrounding fabric of spacetime along with its rotation in a phenomenon called frame dragging, a genuinely strange consequence of general relativity occurring in the immediate vicinity of any sufficiently massive, rapidly spinning black hole. Frame dragging caused by a rotating black hole can cause nearby objects to be gradually pulled into a rotating orbit around it, even without any additional direct force acting upon them. Because the surrounding fabric of spacetime itself is being physically dragged along by a rapidly rotating black hole spin, nearby objects can find themselves gradually swept into a rotational motion purely as a consequence of this spacetime distortion, entirely separate from the black hole's more familiar, straightforward gravitational pull. Black holes are believed to eventually settle into one of only a very small number of possible stable configurations, described by physicists using the informal phrase, black holes have no hair. According to this widely cited theoretical principle, a black hole's final, settled state can theoretically be fully described using only three basic properties: its mass, its rate of spin, and its electric charge, regardless of whatever considerably more complex material or history originally contributed to forming it. The idea that black holes can be fully described using only a small handful of basic properties represents one of the more elegant, surprising simplifications found anywhere within modern theoretical physics. Despite the extraordinarily complex, chaotic processes typically involved in a black hole's actual formation, the resulting object itself is believed to settle into a remarkably simple final state, describable using strikingly few basic physical properties, a genuinely elegant simplification physicists continue to find remarkable. Some physicists continue actively debating deeper theoretical questions surrounding black holes, including what precisely happens to information about matter that falls into one. Known within physics as the black hole information paradox, this ongoing theoretical debate concerns whether information about matter falling into a black hole is ultimately lost forever, an outcome that would directly conflict with certain fundamental principles of quantum physics, representing one of the more genuinely unresolved deep questions found anywhere within modern theoretical physics. Black holes remain, even after more than a century of dedicated theoretical and observational study, one of the most actively researched and still incompletely understood objects found anywhere within the universe. Despite the remarkable observational progress achieved over the past several decades, including direct imaging and the detection of gravitational waves, black holes continue to raise genuinely deep, unresolved questions at the very edge of modern physics, ensuring they remain a rich, active subject of ongoing scientific study well into the foreseeable future. The very first gravitational wave chirp detected by LIGO in 2015 arrived almost simultaneously at both of the observatory's two widely separated detector sites, located thousands of kilometers apart in the United States. Because gravitational waves travel at the speed of light, the tiny difference in arrival time between LIGO's two separate detector locations helped researchers further confirm the genuine cosmic origin of the signal, while also offering a very rough sense of the direction the gravitational wave had originally traveled from. Sound near a black hole's accretion disk, if a person could somehow survive close enough to hear it directly, would likely be an intense, chaotic roar generated by superheated, turbulently swirling gas. While no person could ever survive such extreme conditions, physicists modeling the turbulent, superheated environment immediately surrounding an actively feeding black hole generally describe a theoretically overwhelming, violently chaotic soundscape, driven by extreme turbulence and rapidly shifting magnetic fields within the swirling accretion material itself. Some researchers have created sonifications, meaning audio translations, of black hole data gathered across different types of telescope observations, including X-ray, optical, and radio data combined together. By assigning different pitches or tones to different types of collected astronomical data, researchers have produced various audio translations allowing people to experience black hole observations through hearing rather than sight, an approach increasingly used specifically to make astronomical data more accessible to blind and visually impaired audiences as well. NASA has released numerous black hole sonification projects specifically designed to make complex astronomical data more accessible to a broader public audience, including audiences with visual impairments. Beyond the well-known Perseus cluster sonification, NASA and various partner research institutions have produced numerous additional sonifications translating black hole and other deep space data into audible sound, an ongoing public outreach effort explicitly aimed at making astronomical discoveries considerably more accessible and engaging for a much wider general audience. Sonified astronomical data, including black hole recordings, has occasionally been used in educational planetarium shows and museum exhibits to help general audiences engage more directly with abstract astrophysical concepts. Because translating invisible or inaudible cosmic phenomena into actual sound often makes complex scientific concepts considerably easier to intuitively grasp, planetariums and science museums have increasingly incorporated these audio translations directly into public educational exhibits and presentations focused on black holes and other complex astrophysical phenomena. The gravitational waves detected from black hole mergers carry information not only about the black hole's individual masses, but also about their spin and the overall geometry of their final merger. Because the precise shape, duration, and frequency pattern of a detected gravitational wave chirp depends on multiple different physical properties of the merging black holes, researchers can extract a surprising amount of detailed information from a single detected signal, including estimates of each black hole's individual mass and rotational spin. Some detected gravitational wave signals have revealed black hole mergers occurring in mass ranges astronomers previously considered highly unlikely or even theoretically difficult to explain using standard models of stellar evolution. Because certain detected black hole masses fall within a theoretically predicted gap where standard stellar collapse models suggest black hole formation should be considerably less common, these particular detections have prompted renewed scientific interest in alternative black hole formation theories. Black hole mergers detected through gravitational waves typically occur at extraordinary distances from Earth, often many hundreds of millions or even billions of light-years away. Because gravitational wave detectors are sensitive enough to register even extremely faint distortions in spacetime, they can successfully detect black hole mergers occurring at truly enormous cosmic distances, offering astronomers a genuinely novel window into extremely distant, otherwise completely unobservable regions of the universe. The energy released during a black hole merger, converted briefly into gravitational waves, can very briefly exceed the combined light output of every star in the observable universe. Although this immense burst of energy takes the form of gravitational waves rather than visible light, its sheer magnitude during the final instant of merger genuinely rivals, and can even exceed, the combined luminous output of every single star shining within the entire observable universe, if only for the briefest possible fraction of a second. Some researchers have explored whether extremely sensitive future detectors might one day be able to identify gravitational wave background noise, a faint, continuous hum theorized to arise from the combined effect of countless black hole mergers occurring throughout the universe's entire history. Rather than detecting individual, distinct chirps from specific mergers, this theorized gravitational wave background would represent an extremely faint, constant hum, the accumulated signal from an enormous number of black hole and other massive mergers overlapping continuously throughout cosmic history. Evidence consistent with this predicted gravitational wave background has recently begun emerging through long-term studies tracking extremely precise, rapidly spinning neutron stars called pulsars. By carefully monitoring tiny, extremely subtle timing variations in the otherwise remarkably precise signals emitted by pulsars scattered across the galaxy, researchers have found patterns consistent with the presence of this predicted background hum, offering a genuinely new and different method for detecting gravitational waves beyond the direct chirp-based detections associated with individual mergers. Black hole research continues to rely on an unusual, genuinely interdisciplinary combination of mathematics, observational astronomy, and increasingly, audio and data sonification techniques originally developed for entirely unrelated creative or accessibility purposes. This blending of traditionally separate fields, hard theoretical physics alongside audio engineering and accessible public science communication, reflects just how creatively scientists have needed to adapt in order to meaningfully study and communicate objects as fundamentally strange, invisible, and silent as black holes. As our journey through the strange, quiet sound of black holes comes to a close, perhaps the night sky feels a little different now. Not simply a scattering of distant lights, but a vast, mostly silent expanse occasionally rippling with sound, deep, ancient tones moving through hot gas for billions of years, brief rising chirps marking the final instant of two black holes finally meeting after spiraling toward one another for eons. We've drifted past a note 57 octaves too low for any human ear, past mirrors shifting by less than the width of a proton, past a silence so complete that scientists had to invent an entirely new way of listening just to hear anything at all. Somewhere out there tonight, another black hole is quietly, endlessly turning, wrapped in a silence so deep it makes even the quietest room you have ever sat in feel impossibly loud by comparison. Now you can let all of that drift softly into the background. Let your breathing slow. Let your shoulders loosen. Let the images fade from bright detail into something softer and more distant, like a low, distant hum fading gently into complete and total silence. And if you enjoyed this journey, perhaps you might like, subscribe, or share a thought below. It helps other curious minds find their way here, too, one quiet echo at a time. And if you happen to still be awake, there will be another slow journey waiting for you on the screen, another quiet corner of the universe to drift into gently. But for now, let your mind grow still, and let the day fall away. Sleep well, and good night.